Hello dreamers, greetings from ACE Engineering Academy and ACE Online. Today we are going to discuss the one of the important concept from the subject power electronics and that concept is important for the GATE 2023. Myself, Professor Rajendra Garashe, I have done M.Tech from Indian Institute of Science, Bangalore. I was the All India 7th ranker in the GATE examination and I am working as a faculty member at ACE Engineering Academy, having a subject teaching experience of more than 10 years. So dear students, specifically in this session, we are going to discuss the concept of latching current and holding current and some numericals related to the latching current, holding current, and how it is having relation with the minimum gate pulse width required. Alright? Yeah. So, very first thing is, let us have some discussion on thyristors. We know a thyristor is a family of devices. It consists of 4 layers and 3 junctions. Right? 4 layers are P, N, P and N, and junctions are like J1, J2 and J3. Okay, definitely you all might be familiar with the construction of the SCR. Alright, next, the SCR, that is a silicon controlled rectifier. It is the very first member of the thyristor family. Thyristor is a family of devices. In that, SCR is a one of the member. Alright, how is the construction of SCR? Yes, the construction of the SCR. As I said, it is a 4 layer and 3 junction device. 4 layers are P1 plus, N1 minus, P2 and N2 plus. Right? And the junctions are J1, J2 and J3. Right? 4 layers and 3 junctions. And the 3 terminals are anode, cathode and gate. We know when SCR is in a forward bias mode, junctions J1, J3 are in a forward bias mode, junction J2 is in a reverse bias mode. Right? If we go on increasing the voltage across the anode and cathode of the SCR, and if that voltage becomes equal to VBO, that is the forward breakover voltage of SCR, then the breakdown of the depletion layer across junction J2 takes place and our SCR switch from forward blocking mode to the forward conduction mode. Right? It is like one of the triggering method of a SCR. But it is having a drawback, like it requires a high value of the forward voltage in order to turn on the SCR. So if you want to turn on the SCR at a lesser voltage level, then we need to connect the controlling circuitry between gate and cathode circuit. Right? We know. Next, the symbol of the SCR. Yes, here it is a symbol of the SCR. 3 terminals are anode, cathode and gate. I don't want to go into the operation of the SCR because, as I said, specifically we are going to focus on concept of latching current, holding current and how to deal with the numericals related to the minimum gate pulse width required based on the latching current data. Alright? Yes. Here, VI characteristic of SCR. So, this is the VI characteristic of SCR. Voltage positive, current positive. VA means the voltage across SCR. IA means the current flowing through the SCR. If voltage across SCR is a positive, then it is like your SCR is in a forward bias mode. If voltage across SCR is a negative, then it is like your SCR is in a reverse bias mode. Alright. Now, here if you check, as we go on increasing the forward voltage, what will happen? First of all, my device will block that voltage. Means it is like my device will be in a forward blocking mode. Consider initially gate current is 0, means gate cathode circuit is open. Okay, and if we go on increasing the forward voltage, my device will block that forward voltage, right? Now, theoretically speaking, the leakage current flowing through the device should be equal to 0. But in practical case, some leakage current will flow through the device. That leakage current is known as forward leakage current. As we go on increasing the forward voltage, yes, again my device blocks that voltage. And if forward voltage becomes equal to VBO, that is the forward breakover voltage, it is like the breakdown of the depletion layer across junction J2 occurs and your device will switch from forward blocking mode to the forward conduction mode. Here OM indicates forward blocking mode. During forward blocking mode, your device is characterized with a high voltage and very low or very less current. Okay, during forward blocking mode, I am saying device is characterized with a high voltage and very less current. Less current in the sense it is a comparative only leakage current. It is in the range of microampere. So during forward blocking mode, device voltage is high, that is voltage across device is high, current flow through the device is low. So what is the impedance offered by the device? Impedance offered by the device, we know impedance is nothing but voltage divided by current. So impedance offered by the device is also high. Means it is like your device is in open circuit mode, straightforward. Alright. Next, when the forward voltage across device is equal to VBO, then your device switch from forward blocking mode to the forward conduction mode. Yes, this, let me mark it as NK. Suppose this is your NK. NK indicates your device, NK indicates device is in a forward conduction mode. Forward conduction mode means device is in a on state. Device is in a on state. Alright. Next, so this dotted line M to N, that dotted line indicates it is a transition from forward blocking mode to the forward conduction mode. Right. Blocking mode to the conduction mode. Next, now if we want to turn on the device at a lesser voltage level, then we need to take the help of gate current. We need to take the help of gate current. Suppose this is VBO3. Let me write this as IG3, so I am writing it as VBO3. VBO3 is less than VBO. So if I want to turn on the device at this voltage level, at this forward voltage, I need to take the help of the gate current. Right? Similarly, if I want to turn on the device at a further reduced voltage level, I need to again take the help of the gate current. Here, as forward voltage decreases, forward voltage across device decreases, the required gate current to turn on the device will increase. Okay, required gate current to turn on the device, it increases. Alright, and similarly you might be familiar with this relation. Next, second here, the third quadrant characteristic, it indicates your device is in a reverse bias mode. Right, device is in a reverse bias mode. So this O to X, let me write it as point OX or OP. The curve OP indicates device is in a reverse blocking mode. Device is in a reverse blocking mode. Means we are applying the voltage across, reverse voltage across the device, and my device is blocking that voltage. We know when device is in a reverse bias mode, which junctions will be in a reverse bias mode? When SCR is in a reverse bias mode, junctions J1, J3 reverse bias, junction J2 forward bias. And we know as the lightly doped layer is a part of junction J1, so your junction J1 can block a high value of reverse voltage. Junction J3 will not block a high value of reverse voltage. Okay, so when SR is in a reverse bias mode, your junction J1 can block a high value of reverse voltage. Right, junction J3 is not having the high voltage blocking capacity. Alright, next, now yes, suppose SR is in a reverse bias mode and we are increasing the reverse voltage across the device. What will happen? My device blocks that voltage, my device blocks that reverse voltage. And this current, you can check, this current is a reverse leakage current here. So during reverse blocking mode, device is characterized with a high voltage and very less current, that is a leakage current. So impedance offered by the device is again, it is a high impedance. During forward conduction mode, NK indicates forward conduction mode. During forward conduction mode, device is characterized with a comparatively less voltage, very less voltage. It is like on state voltage drop. and high current. You can check any operating point on a NK curve, the current value is high, voltage value is comparatively less. So during forward conduction mode, device is characterized with the less voltage or low voltage or small voltage and high current. So small voltage and high current means impedance offered by the device is, again it is a low impedance and means device is in a on state. Yes or no, right? So we are having three modes of operation: forward blocking, forward conduction, reverse blocking. We don't have reverse conduction mode. Be careful. We don't have reverse conduction mode. If I apply this much of voltage, across the device, what will happen? The breakdown of the reverse bias junctions J1, J3 takes place and suddenly very high current will flow through the device. This high current will surely damage your device permanently. This vertical line characteristic is only for the theoretical understanding. We cannot control this current in practical way. Practical case. Alright? If you maintain this much of voltage across device, your device will surely get damaged. So that's why if you check, the manufacturer of the device generally suggests don't operate the device at this voltage. It is better to operate the device at somewhat lesser voltage. This voltage indicates the voltage rating of a device. This voltage indicates the voltage rating means voltage blocking capacity of a device. Voltage rating of a switching device indicates the voltage blocking capacity of a device, right? Means how much voltage my device can block, right? That indicates your voltage blocking capacity, that is a voltage rating of your device. Alright, so please keep in mind, if you maintain this much of voltage across your SCR in a reverse bias mode, your SCR will get damaged permanently. Alright, yes. So here let me highlight some points. We are having total 3 modes of operation. First one, yes, modes of operation. I am only giving the overview of SCR operation, right? Yeah. Because our main task is to discuss the latching current and holding current specifically. So first mode, forward blocking mode. During forward blocking mode, yes, SCR is characterized with a high voltage and very small current. High voltage and small current. So if voltage is high, current is small. So what is the impedance? Impedance is high and high impedance. Alright, forward blocking mode. Second mode is forward conduction mode. Yes. During forward conduction mode, how the SR is characterized with forward conduction, low voltage and high current, right? You can check voltage across device is very less na. This is your voltage axis. So voltage across device is low and current is high, right? So it is less voltage or small voltage, high current. What are the impedance? Yes, low impedance na? Low impedance. And third one is reverse blocking mode. Yes. Reverse blocking mode. During reverse blocking mode, SR is characterized with a high voltage and low current or small current. High voltage and small current or low current. High voltage, small current. So what is the impedance? High impedance, right? And it is a high impedance. We don't have reverse conduction mode, all right? Yes. Next, let us discuss the latching current and holding current. Latching current and holding current definitions. Yes, latching current. It is the minimum anode current required to maintain SR into on state immediately after SCR has been turned on using gate signal and gate signal has been removed. Okay, means first of all let me write this definition. It is minimum anode current. It is minimum anode current required to maintain SCR into on state. It is minimum anode current required to maintain SR into on state immediately after SCR has been turned on. SCR has been turned on using gate signal or gate current and using gate signal and gate signal has been removed. Let us understand this. Latching current means it is a minimum anode current required to maintain SCR into on state immediately after SCR has been turned on using gate signal and gate signal has been removed. For example, suppose this is my SCR. So first thing we know from the operation of SCR is a semi-controlled switch. We can turn on the SCR by using the gate signal or gate current. But when SCR turns on, after that, if I remove the gate signal, my SCR will not come back to the off state. So that's why SCR it is like a latching device. SCR is a semi-controlled device, semi-controlled switch. We can turn on the SCR by using the gate signal. But if I remove the gate signal, my SCR will not turns off. Therefore, it is known as a semi-controlled switch. Now, let us understand the latching current. Suppose this is my SCR, right? This is my SCR. So, I am turning on this SCR by using the gate signal or a gate triggering. We know in a SCR we are having the various turn on methods. Out of that, the most popular method is a gate triggering. Alright? Yes. Suppose this is my SCR. Initially, it is in an off state. Now, I am turning on this SCR by using the gate signal by circulating the gate current in a gate cathode circuit of SCR. Alright. Now, suppose I have circulated the gate current in a gate cathode circuit of SCR and now my SCR has turned on. As we know, SCR is a semi-controlled device. SCR is a latching device. Once my SCR turns on, after that I can remove the gate signal. Yes or no? Right? Once SCR turns on, your gate signal loses the control over SCR. Alright? Now, this is my SCR. I am turning on this by using the gate signal. Alright? Suppose by circulation of the gate current, we have turned it on and my SCR is now in a on state. Now, at the instant of removal of the gate signal, what is the value that should be flowing through the SCR? What is the minimum value that should be flowing through the SCR in order to maintain the SCR into on state? Is nothing but your latching current. Means latching current means it is the anode, it is the value of the current that should flow through the SCR at the instant of removal of the gate signal, right? So at the instant of removal of the gate signal, what is the minimum value that should flow? Minimum value of current that should flow through the SCR, that is nothing but the latching current. Suppose I have turned on the SCR by using the gate signal, okay, and now at the instant of removal of gate signal, if my SCR current is less than the latching current, then my SCR will not maintain, will not continue into the on state. Are you getting the point? Means latching current means it is the minimum value of anode current that should flow through the SCR at the instant of removal of the gate signal. That is nothing but the latching current, right? Second, let us discuss the holding current. Holding current. It is minimum anode current. It is minimum anode current required. It is minimum anode current required to maintain SCR. It is minimum anode current required to maintain SCR into on state. Otherwise it turn off. So if you check the definitions, latching current, holding current, these are very confusing. But one point is, in the holding current definition, they have not mentioned anything regarding the gate triggering or the gate signal, right? So it is the minimum anode current required to maintain SCR into on state. Otherwise it will turn off. The meaning is, suppose this is my SCR. I have turned it on at morning 6. Let us consider this is my SCR. I have turned on this SCR at morning 6. Okay, at morning 6 o'clock, I have turned it on by using the gate signal. And after 5 minutes, once my SCR turns on, after that, within a 5 minutes, I have removed the gate signal. And from that instant, my SCR till this time, my SCR is continuing into the on state. Now, if I want to turn off this SCR, then my current flowing through the SCR should be less than the holding current value, right? If I want to turn off the SCR, I need to reduce the current flowing through the SCR below the holding current value. That is nothing but your holding current. Means this is my SCR. I have turned on this SCR at a morning 6 o'clock. And within 5 minutes, I have removed the gate signal. After that, my SCR is continuing into the on state. If current flow to the SCR becomes less than the holding current value, then again my SCR will come back to the off state, right? And that current means, in order to turn off the SCR, how much current we require? We require a holding current. So please listen, latching current means at the instant of removal of the gate signal, what is the minimum current required to flow through the SCR? That is nothing but the latching current in order to maintain SCR into on state. Holding current means I have turned on the SCR at the morning 6 o'clock and within 5 minutes I have removed the gate signal. From that instant my SCR continuing into the on state. And if current flowing through the SCR becomes less than the holding current value, my SCR will again come back to the off state. That is nothing but the holding current value. Generally, holding current is associated with the turning off of a SCR. Latching current is associated with the turning on of a SCR. Generally, latching current value is greater than the holding current value. Alright. So here, yes, at the instant of removal of the gate signal, what is the minimum current that should flow through the SCR? in order to maintain your SCR into on state, that current is nothing but the latching current. My SCR is turned on earlier, right? Long back I have turned on the SCR. Even I have removed the gate signal also. And after that my SCR is continuing into the on state. If I want to turn off the SCR now, then I need to reduce the current flow to the SCR below the holding current value. Then my SCR turns off. Alright. So these are the two definitions, latching current and holding current. In a holding current definition, they have not mentioned anything regarding the gate signal or gate triggering. But in latching current definition, yes, specifically they have mentioned about the gate triggering or gate signal. Alright? Yes. Now we are going to discuss some numericals related to the minimum gate pulse width required and based on your latching current value. Okay, let us discuss. Yes. The latching current of the thyristor shown in the figure is 5 milliampere. Latching current they have given. The minimum duration for which gate current should be maintained is, means we need to find the minimum duration for which the gate current should be maintained is. And they have given this circuitry. Alright. So simple circuit, it is a DC excitation and resistor and inductor. DC excitation and we are having the RL branch. Alright. And here it is a SCR. Let us discuss how to simplify. This type of questions they have asked in a previous GATE as well as ESE examinations. Okay. Right. Yeah. So in order to simplify this, we need to understand the definition of latching current. So I need to maintain the gate signal in the gate signal to the SCR. I need to maintain gate signal means I need to circulate the gate current in a gate cathode circuit of SCR till the current flow to the SCR reaches which value? Latching current value. Till current flow to the SCR reaches latching current value. Alright? Yes. Let us discuss this. Here consider for t less than 0, your circuit will be at a rest position. Means it is like this SCR is in a off state. Okay, let me write for t less than 0. For t less than 0, consider SCR is in a off state. So for t less than 0, if your SCR is in a off state, tell me when this is in a open circuit mode, what is the current flowing through the circuit for t less than 0? If this is open circuit, circuit current will be definitely 0. Alright. So here circuit current I is equal to 0 ampere. This is for t less than 0. Alright. Now suppose at t equal to 0, we are applying the gate pulse to this SCR. We are applying the gate signal to the SCR. And my SCR is as turned on. Okay. At t equal to 0. At t equal to 0. Gate pulse is applied to SCR. At t equal to 0, gate pulse applied to SCR. So if we apply the gate pulse to the SCR, definitely our SCR will turn on. So SCR turns on. SCR turns on. Yes, but for turning on of SCR, we require one basic thing, that is SCR should be in a forward bias mode. Na? If SCR is in a reverse bias mode and if I apply the gate signal, whether my SCR will turn on? No. Alright. So here you can check, this is the positive plate of the battery, this is the negative plate of the battery. Positive plate through this RL branch is connected here. Negative plate is connected at this side. Okay. So it is like anode of the SCR will be definitely at a higher potential than that of the cathode. Means your SCR is in a forward bias mode only. And we are applying the gate pulse to the SCR. So definitely my SCR will turn on. Alright, now tell me at t equal to 0, this SCR turns on. But what is the status of this inductor? Come on, recall the network theory, network analysis. In that transient response chapter we are having. If before the switching instant, current flowing to the inductor is 0, then at the switching instant your inductor acts as an open circuit, na? Right? So at t equal to 0, this will act as an open circuit. This will be in on state, no doubt. Yes, there is an on state, but this will act as an open circuit. Inductor will act as an open circuit. So let me draw. Right? So circuit will be like this. Inductor will act as an open circuit. SCR on state. This is DC excitation. Yes, 80 volt. This is 1000 ohm. This current is I. Here it is inductor, which is open circuit, and here it is a SCR. Alright. So here, yes, here what is happening? Inductor acts as an open circuit, right? Inductor acts as an open circuit. So if inductor acts as an open circuit, then what is the circuit current? I is equal to 0 ampere. Circuit current I is equal to 0 ampere. At t equal to 0, this circuit current will act as an open is equal to 0. All right. Next, for t greater than 0, what will happen? Yes, for t greater than 0, we know from the network transients, for t greater than 0, resistor will act as a resistor, inductor will act as an inductor, SR will be on state, right? So yes, we can draw the circuit. It is a 80 volt. Here it is a resistor, inductor and SCR. Alright, we will be having this type of circuit. This is 1000 ohm. Inductor value is 0.062 Henry. 0.062 Henry. And this is SCR. And circuit current is I. Now, we need to simplify this circuit. Definitely we can write the KVL equation, and by using the Laplace transform we can simplify. But I suggest it is simply RL branch, across that we are putting a DC excitation. When a DC excitation is connected across the RL branch, we are having some standard current expression in a circuit. I think in network theory as well as in control systems, you might have come across this type of circuits. We are having RL circuit, RC circuit, okay? DC excitation connected across RL branch, DC excitation connected across RC branch. In those cases, we are having some standard expressions. Now, here I am going to derive this expression, but at the end, I will tell you how to memorize this expression, okay? Because it is simple, okay? If you memorize that expression in RL branch DC excitation, okay? If you memorize that expression, so that in the final examination, that will save your time, all right? Yeah. So let us simplify this. Apply KVL to loop. So it is, so instead of 80 volt, I am writing it is in terms of Vs. I am writing this in terms of Vs. General term I am writing here, okay? Right. So apply KVL, plus Vs minus R into I minus L into di by dt equal to 0. Plus Vs minus Ri minus L into di by dt equal to 0. Alright. So therefore Vs equal to Ri plus L into di by dt. So now you can simplify this either by using the Laplace transform, or you can simplify this by using the conventional method of solution of differential equations, like finding the integrating factor and so on, okay? Let me simplify this by using the Laplace transform, okay? Right. Taking Laplace transform on both sides. So I am taking the Laplace transform on both sides. So it is Vs by S. So it is a Vs by S is equal to R into I of S plus Ls into I of S. So therefore Vs by S is equal to R plus Ls into I of S. Let us take this L outside. So therefore Vs by S is equal to L into S plus R by L into I of S. So from this we can write I of S equal to, yes, therefore I of s is equal to Vs by L into, I am writing this as 1 upon S into S plus R by L, right? Now we need to simplify this with the help of partial fractions, okay? So I am going to find the partial A and B coefficients for this term, okay? Right, so we can write this as I of s is equal to, yes, Vs by L I am writing into 1 by S plus, sorry, A by S, not 1, it is A by S plus B upon S plus R by L. Alright, let us find the A and B values, okay? A is equal to, yes, we can write L by R. A is equal to L by R. And what is B? B is equal to, it is a minus L by R. So if I put A and B values here, yes, we will be getting I of S. Therefore, I of S is equal to Vs by L into L by R upon S minus L by R upon S plus R by L. Alright. Next, let us put this L or take L by R common from the numerator. So I can write it as it is equal to Vs by R into 1 by S minus 1 upon S plus R by L. Let us take the inverse Laplace transform. Taking inverse Laplace transform, so we can get I is equal to Vs by R into, yes, 1 minus t to the power minus RT by L. Alright, RT by L. This is the expression for current in a circuit. So here if you check this expression in current, expression of current in circuit is Vs means supply voltage divided by resistance into 1 minus e to the power minus t by tau. This is a RL circuit now. We are having the DC excitation across RL branch. So for the RL branch, what is the time constant tau? Tau equal to L by R. So it is like, yes, I is equal to Vs by R into 1 minus e to the power minus t by tau, right? Minus t by tau. So this is the standard expression. If you put a DC excitation across the RL branch, you can directly memorize this expression so that it will save your time. It will save your time. Alright. Now this is my current expression in a circuit. Here, let me put that Vs, R and L values. Okay. Right. Now I can get here I equal to Vs is 80 upon R is 1000 into 1 minus e to the power minus RT by L minus 1000 into T upon L is 0.062, 0.062, right? This is the expression for current in a circuit. Alright, we can write in fraction even, right? So it is equal to I equal to 80 upon 1000 means 0.08 into 1 minus e to the power, I am keeping this as it is, minus 1000 into t upon 0.062. Now this is the current which is flowing in a circuit. You can check when t equal to 0, this term will become e to the power 0 is 1, 1 minus 1 0, current in a circuit is 0. After that, as time increases, this term go on decreasing, right? This term go on decreasing. So therefore 1 minus this term, this difference go on increasing, current go on increasing, current go on increasing. So if you check, the current in a circuit is having the nature like this. Circuit current is having this type of nature. Steady final value is Vs by R, which is equal to 0.08 only. And yes, we need to maintain the gate signal Ig. Till which time we need to maintain the gate signal? Yes, let us discuss. At t equal to 0, we have applied the gate signal na? But till which time we need to maintain the gate signal? We need to maintain the gate pulse. Let us discuss. As per the definition of latching current, we need to maintain the gate signal or gate pulse till the circuit current reaches which value? Latching current value. So this is 0, this is 0.08. My SCR latching current is 5 milliampere. Okay, latching current is 5 milliampere. So suppose somewhere it is starting from 0 now. So after some time definitely it will reach to which value? Latching current value. Suppose this is my latching current. So till your SCR current reaches the latching current value, we need to maintain the gate pulse to the SCR. Please try to understand this. Till your SCR current reaches the latching current value, we need to maintain the gate pulse to the SCR. If I remove the gate pulse before this TP means it is a minimum gate pulse I am saying, okay. If you remove the gate pulse before TP, your SCR will not be maintained into the on state. You can continue gate pulse after TP also, no doubt. But they are asking the minimum gate pulse. So minimum gate pulse means we need to maintain the gate pulse till SCR current reaches which value? Latching current value. Right? Now simply from this expression, we can write at T equal to TP, what is I value? I value is IL. Okay? So at T equal to TP, I is equal to IL. So therefore I am writing IL equal to 0.08 into 1 minus e to the power minus 1000 into TP upon 0.062. Right? At T equal to TP, I am replacing here T with TP and I have replaced the I with the IL. What is IL value? IL value is 5 milliampere. Na? They have given. IL is a 5 milliampere. Alright? So it is a 5 milliampere. 5 into 10 to the power minus 3. 0.08 into 1 minus e to the power minus 1000 into TP upon 0.062. Right? So it is simple, one equation, one unknown. We can solve this. Okay? So after solution you will get TP equal to 4 microsecond. TP equal to 4 microsecond. Alright? Yes. You need to take that natural log at somewhere and you will get the answer. Okay? So 4 microsecond, you will get the answer. Right? Yes. So how to simplify? From this example, you will understand what is the latching current actually. Right? We need to maintain the gate pulse to the SCR till SCR current, not the circuit current, till SCR current reaches the latching current value. Till SCR current reaches the latching current value. Definitely in this numerical, we had only one loop. So circuit current is nothing but only SCR current. Let us discuss one more case. Yeah. This question is from gate 2006. Now, if you check in this circuit, we are having the two loops, na? First and here it is second. They have given two parallel branches here. And SCR having a turn on time of 5 microsecond, latching current of 50 milliampere and holding current of 40 milliampere is triggered by a short duration pulse and is used in the circuit shown in figure. The minimum pulse width required to turn on the SCR will be. They are asking again TP value. Minimum pulse width means what is the minimum TP, that is minimum value of the gate pulse width. Okay, right. So till the instant your SCR current reaches latching current value, we need to maintain the current in circuit or gate signal, right, to the SCR. Okay, right. So here, yes, suppose this current is I, this current is I1 and this current is I2. Okay, I1 and I2 I am writing. Now definitely for t less than 0, this circuit current will be 0, right? SCR current will be 0, right? At t less than 0, SCR off state. Okay, so I am writing here. For t less than 0, SCR will be in a off state. So what is circuit current? I1, I2 all are 0, right? This is open circuit, so excitation here circuit here, right, remaining part, your current will not flow from source towards this side. So I1, I2 all are 0. All right. Next, at t equal to 0, at t equal to 0, gate pulse is applied to SCR. Gate pulse is applied to SCR. Gate pulse is applied to SCR. So at t equal to 0, we are applying the gate pulse to SCR, means my SCR will turn on, na? Right? What is the status of this inductor at t equal to 0? Inductor will act as an open circuit. Resistors will act as an resistors only. Okay, so let me draw the circuit. At t equal to 0, your circuit will be like this. R. This is open circuit. And here it is second branch resistor, right? 100 volt. This is SCR. This current is I, 20 ohm, I1, I2. Here it is inductor which is acting as an open circuit, and here it is 5000. 5 kilo ohm means 5000 ohm. Now tell me what is I1 value here? I1 is 0. What is I2? I2 is 100 divided by this 5000, na? Right? 100 by 5000. So it is 100 divided by 5000. So it is equal to 20 milliampere. So I2 is equal to 20 milliampere. I2 equal to 20 milliampere. At t equal to 0, I2 is 20 milliampere. I2 20 milliampere, what is I? Simply apply KCL here. You will get I equal to I1 plus I2. Alright. So therefore, what is I? I is equal to I1 plus I2. But I1 is 0. So it is 20 milliampere only. So SCR current is 20 milliampere. SCR current is 20 milliampere. Alright. Yes. Now, yes, if you check, my SCR is having the latching current of 50 milliampere, na? Right? Now, for t greater than 0, how is the circuit? For t greater than 0, this is on state. Resistor will act as a resistor. Inductor will act as an inductor. So, for t greater than 0, for t greater than 0, yes, circuit will be like this. SCR on state, resistor, inductor, and here it is another resistor. All right. This is 100 volt. SCR, current I. This is 20 ohm resistor. Inductor value is 0.5 Henry. So it is 0.5 Henry. And this resistor, the branch currents. I2 we can directly write, na? This 100 volt will appear across this 5000 ohm resistor. So I2 is 100 by 5000. Okay. I2 is equal to 100 upon 5000, which is equal to 20 milliampere. 20 into 10 to the power minus 3 ampere, right? 20 into 10 to the power minus 3 ampere. This is I2. What is I1? You can check. We can directly write the expression of I1. Across RL branch, directly we are having the DC excitation, na? Right? So, I1, I am writing I1 is equal to, this is Vs means 100 divided by resistor present is 20 into 1 minus e to the power minus RT by L. R is 20 into T upon L is 0.5. So it is equal to 5 into 1 minus e to the power minus 40 into T. This is my I1, right? So what is this SCR current I? I is equal to I1 plus I2. I equal to I1 plus I2, which is equal to I1 is 5 into 1 minus e to the power minus 40t plus I2 is 20 into 10 to the power minus 3. 20 into 10 to the power minus 3. So it is equal to 5.02, right, minus 5 into e to the power minus 40t. This is current I, right? This is a current I. Current in a circuit, that is SR current, all right. Now, if you check this current I waveform, how it will be? At t equal to 0, what is current? T equal to 0, if you check, this is e to the power 0 means 5 into e to the power 0 is 5. So 5.02 minus 5 means it is 0.02, that is 20 milliampere. So at t equal to 0, it will be having 20 milliampere means 0.02 ampere value. After that, it go on increasing and it will reach the final value. All right. Now, how is the Ig? Ig is like this. Right? Yes, we need to maintain the gate signal till SR current reaches which value? Latching current value. So suppose somewhere it will reach the latching current value. Alright. So this we need to find Tp. How to find? At t equal to Tp. At t equal to Tp, I is equal to IL. Simply put in this expression, replace T with Tp, replace I with IL. Okay. At t equal to Tp, I is equal to IL. So we can write IL is 50 milliampere. 50 into 10 to the power minus 3 is equal to 5.02 minus 5 into e to the power minus 40 into Tp. Alright. So one equation, one unknown. From this we can find Tp. Right? We can find Tp. So therefore, yes, 5 into e to the power minus 40 into Tp is equal to 5.02 minus 0.05. So we can simplify this. So therefore, taking natural log on both sides, or let me first shift this t. If I shift this 5 to right hand side, we will be getting it as e to the power minus 40 into Tp is equal to 4.97 divided by 5. It is 0.994. Now how to simplify this? Natural log on both sides. Taking natural log on both sides. So therefore I can write minus 40 into Tp is equal to natural log of this 0.994. So it is a natural log of 0.994. Yes, minus 6.018 into 10 to the power minus 3. So minus will get cancel out. So therefore what is Tp? Yes, from this we can find Tp. It is 150 microsecond. Alright, 150 microsecond. So like this you need to simplify, right? Yeah. Next, let us discuss this question. Yeah, one different kind of question. As such, in the previous question papers they have not asked this type of questions, but let us discuss how to solve if they ask. An SCR having a turn on time of 10 microsecond. SCR turn on time is 10 microsecond. Latching current is 50 milliampere. Is triggered by a short duration pulse and is used in the circuit shown in figure. The minimum pulse width required to turn on the SCR will be. Now if you check in this circuit, we are having only DC excitation, resistor and directly SCR they have given. If you check for t less than 0, SCR is in an off state. What is circuit current? 0. Let me write. For t less than 0, SCR off state. If SCR is in an off state, what is circuit current? Circuit current is a 0 ampere. For t less than 0, circuit current is 0. At t equal to 0, SCR turns on. At t equal to 0, we are applying the gate pulse to SCR. Gate pulse is applied to SCR. Gate pulse is applied to SCR. So if the gate pulse is applied to SCR, your SCR will turn on. SCR turns on. SCR turns on. Alright. So now if SCR turns on, now tell me at t equal to 0, how is the circuit? At t equal to 0, this will act as a short circuit, that is a on state device. And this will be resistor, will act as a resistor. So my circuit is like this. Here it is 80 volt and SCR. Alright. So this is 80 volt. Here it is 100 ohm. And here it is SCR. And circuit current is I. Now tell me at t equal to 0, what is circuit current I? I is equal to 80 by 100. Alright. I is equal to 80 by 100. Which is equal to 0.8. Right. 0.8 ampere. So circuit current at t equal to 0 is 0.8 ampere. Alright. Means how is the circuit current waveform? You can check this type of circuit current waveform will be getting. At t equal to 0, your circuit current will reach suddenly to the non-zero value. This is 0.8 ampere. And now tell me, what is the latching current of my SCR? My SCR latching current is 50 milliampere. So 50 milliampere means somewhat here. So at t equal to 0, immediately your SCR current is rising from 0 ampere to the 0.8 ampere. So how to find TP? So in these cases, please try to understand. If this is the case, then you need to maintain the gate signal to the SCR till the turn on time of SCR. Okay. So I am writing minimum gate pulse width. Minimum gate pulse width is equal to TP. In this case, it is a T on is equal to T on. What is the on time? Device turn on time? 10 microsecond. So we need to maintain gate pulse till the 10 microsecond. Right? 10 microsecond. So let me note this. SCR gate pulse width. Gate pulse width should fulfill, gate pulse width should fulfill following conditions. Following conditions. Gate pulse width should be greater than or equal to time. Gate pulse width should be greater than or equal to time required for SCR. Sorry, time required for SCR current. Time required for SCR current. Time required for SCR current to reach latching current. To reach latching current value. And second condition is TP should be greater than or equal to. Here it should be and, not or. It is a and. And TP should be greater than or equal to turn on time of device. Turn on time of a device. So your SCR gate pulse width should fulfill these two requirements. Now in this case, if you check, what is the time required for the SCR current to reach the latching current value? It is hardly 0 second. In 0 second it is changing, reaching from 0 to the 0.8 ampere. 0.8 is greater than the latching current value. So here, but in this case, your turn on time is 10 microsecond. 10 microseconds is greater than your 0 time. So therefore, we need to maintain the gate pulse till 10 microsecond. Alright. So these are the two important requirements for your gate signal. So friends, this is about the discussion of minimum gate pulse width required based on the latching current and the turn on time of a device. Alright.